Good morning. Today I will discuss second part of linear transformation or linear mapping. Actually, I already post in my channel three different videos on this topic. The first video defines what is linear transformation or linear mapping. I showed in that video the definition of linear mapping and few examples to demonstrate whether a mapping is said to be linear mapping or it is just a mapping. In the second video, I did kernel of a linear mapping, image of a linear mapping, and some examples related to the topic. Today, I will discuss dimension of ker-T or kernel of T and dimension of image of T. And the main part of today's video is matrix representation of a linear mapping, which is quite interesting and very much important related to linear transformation or linear mapping. Now, I want to say few new words. ker-T is also known as null space of T, which is denoted by n of T, and image of T or imT is known as range of T, denoted by R of T. So the another name of ker-T is n of T or null space of T, and image of T is known as range of T or R of T. The dimension of ker-T is called nullity of T, where the dimension of imT is called rank of T. Okay, just remember these two terms. Dimension of ker-T is known as nullity of T, and dimension of imT is known as rank of T. Again repeating, dimension of ker-T is known as nullity of T, and dimension of imT is known as rank of T. Now there is a very important theorem. The theorem states that dimension of ker-T plus dimension of imT equals to dimension of the vector space V. What is V? Actually, the linear transformation is defined in such a way that the domain set is V and the codomain set is W. So the summation of dimension of ker-T and dimension of imT equal to dimension of V, or other words we can say nullity of T plus rank of T equals to dimension of V. I will not prove this theorem in this video, otherwise the video will be quite lengthy. We just remember the theorem, the result of the theorem. Now in my previous videos, I did some problems related to ker-T of a linear mapping and image or imT of a linear mapping. I was given two examples, one example for image and another example for ker-T. In this tutorial, I want to show one particular example, and in this particular example I will have to find imT, ker-T, rank of T and nullity of T all together. Alright, so to do so, first what is given? Okay, the question is let T maps R3 to R3 be defined by T of x comma y comma z equals to x plus y minus z, comma 2x minus y plus z, comma x minus 2y plus 2z. find empty, car T, rank of T, and nullity of T. So given T maps R3 to R3 such that T of xyz equals to x plus y minus z, comma 2x minus y plus z, comma x minus 2y plus 2z. Mark this as equation number 1. To find car T, let us take car T equals to xyz such that T of xyz equals to 0, 0, 0, because we know car T is a subset of capital V or domain set, so that the images of every element of car T is null element 0 which belong to the codomain set W. In other words, we can say car T is the subset of V which contains all the pre-images of the element theta belongs to W. So according to definition, xyz are those elements such that the linear transformation of xyz equals to 0, 0, 0. Alright. Now we have to find xyz. To do so, I have to write the value of t of xyz by equation number 1, x plus y minus z, comma 2x minus y plus z, comma x minus 2y plus 2z. That is equals to 0, 0, 0. By comparing, we get x plus y minus z equals to 0, 2x minus y plus z equals to 0, x minus 2y plus 2z equals to 0. Now we have to solve these three equations for the values of x, y, z. So I just consider these two equations and doing cross multiplication method. You can apply Cramer's rule, you can apply elementary row operations, you can apply matrix inversion method, but this is quite handy method. So by solving these two equations, I get x by 0 equals to y by minus 3 equals to z by minus 3. Dividing the denominators by minus 3, we get x by 0 equals to y by 1 equals to z by 1 equals to lambda say, where lambda is a real number. So from these equations, we get x equals to 0 into lambda equals to 0, y equals to 1 into lambda, that is equals to lambda, z equals to 1 into lambda equals to lambda. So what is xyz? Xyz equals to 0, lambda, lambda, taking lambda as common, 0, 1, 1. Now see, xyz can be expressed as some linear combination of 0, 1, 1. Because whatever value of lambda, we can find xyz, where lambda is a real number. Now, as xyz is an arbitrary element of car T, and xyz can be expressed as a linear combination of 0, 1, 1, then we can definitely say that every element of car T can be expressed as a linear combination of 0, 1, 1, because xyz is arbitrarily chosen. So in other words, we can say car T can be generated, or all the elements of car T can be generated by the help of 0, 1, 1. Therefore, we can write car T equals to linear span of 0, 1, 1. Again, 0, 1, 1 is a single element, and we know single element is always linearly independent. Therefore, dimension of linear span of this is 1. That is, dimension of car T is 1. That is, nullity of T is 1. Okay. So we have kernel of T, that is this. We have nullity of T, that is 1. Next, we have to find image of T and rank of T. Image is a subset of the codomain set. The definition of image was the elements of the codomain set will form a subset, or will say it will the elements of the codomain set will form image set of T if they have pre-images in the domain set V. Okay, means those elements of W which have preimages in V will form a subset of W. That subset of W is known as image of T. So according to the definition, let us consider image of T equals to T of xyz such that xyz belongs to R3, because here R3 is V and R3 is W. Now we consider an arbitrary element xi from Mt, right? We consider an arbitrary element xi from Mt such that xi equals to this element T of xyz. Now what is T of xyz? T of xyz is x plus y minus z, comma 2x minus y plus z, comma x minus 2y plus 2z, because it is given in the question. Now we have to split this in three different elements form. See, x comma 2x comma x plus y comma minus y comma minus 2y plus minus z comma plus z comma 2z. Taking x common, we have 1 to 1 plus y 1 minus 1 minus 2 plus z minus 1 1 2. If we take minus 1 common from the second part, we'll have x 1 to 1 minus y minus 1 1 2 plus z minus 1 1 2. Now see carefully, we have this element and this element are unequal, but these two are equal elements. So whenever we consider, we have to consider only one among these two, because these two are same elements. Okay, so we can say that xi can be expressed as some linear combination of 1 to 1 and minus 1 1 2. Okay, xi can be expressed as a linear combination of 1 to 1 and minus 1 comma 1 comma 2. Again, xi is an arbitrary element of Mt. So we can say every element of Mt can be expressed as some linear combination of 1 to 1, comma, minus 1, comma 1, comma 2. In other words, 1 to 1, comma minus 1, comma 1, comma 2 spans the set Mt. That is, Mt equals to linear span of 1 to 1, comma minus 1, comma 1, comma 2. So we have image of T. Now we have to verify whether these two elements are linearly dependent or independent. We know that two elements are said to be linearly dependent if they can be expressed like this. Means 1 to 1 equals to some constant into minus 1 comma 1 comma 2, or minus 1 comma 1 comma 2 equals to some constant into 1 comma 2 comma 1. And in the both cases, we cannot express for any arbitrary value, right? Means these two elements are actually not linearly dependent. That is, they are linearly independent. Therefore, we can say as these two elements are linearly independent, dimension of this set is 2. That is, dimension of Mt is 2. In other words, rank of T is 2. Okay. So this is the complete result of this question. Now I have to show that this theorem holds. What is nullity of T here? Here nullity of T is 1. Just remember, what is nullity of T here? 1. What is rank of T here? Here rank of T is 2. So nullity of T plus rank of T equals to 1 plus 2, that is equals to 3. Now what is the dimension of V? Here what is V? Here V is R3. So dimension of R3 is this 3, and dimension of W is also 3. As the dimension of R3 equals to 3 and nullity of T plus rank of T equals to 3, then we can easily say that nullity of T plus rank of T equals to dimension of R3, which indicates that the above theorem is completely true. So just remember the theorem. Now, in my last video, I was given few examples to verify whether a mapping is a linear mapping or not. In that videos or examples, some functions or some mappings are given. Now come to my next example, which is quite interesting. The example is here the function is already known as a linear function, but the function or linear mapping is not given. We have to form or we have to find the linear mapping. So how to do so? The question is, a linear mapping T maps R2 to R2 be such that T of 2 comma 3 equals to 4 comma 5, means 2 comma 3 has image 4 comma 5, and T of 1 comma 0 equals to 0 comma 0. Here 2 comma 3 comma 1 comma 0 is a basis of R2. Describe the linear transformation. Now what is basis? Okay, I will tell you. First, start the problem. Given T maps R2 to R2 is a linear transformation, let x comma y belongs to R2, right? Now T of 2 comma 3 equals to 4 comma 5 given, and T of 1 comma 0 equals to 0 comma 0. So can we draw this? This is our R2, that is domain set, and this is our R2, that is codomain set. Means this is our W and this is our this is our V and this is our W. Now 2 comma 3 and 1 comma 0 belongs to this set, and 4 comma 5 0 comma 0 belongs to this set. Now the image of 2 comma 3 is 4 comma 5 and the image of 1 comma 0 is 0 comma 0 with respect to the linear mapping T. It is also said that 2 comma 3 and 1 comma 0 is a basis of R2. Now what is basis? Actually basis is a set whose each and every elements are linearly independent, and by the help of the elements of the basis we can generate the whole domain set. Okay, I'm repeating. Basis is a set which contains elements are linearly independent, means we can say that they are mutually linearly independent, and by the help of the elements, by taking linear combinations of the elements of the basis, we can generate the whole domain set or codomain set. Here the basis is a basis of R2, means these two elements can generate R2 completely and this R2 completely. Now we have to find the function first. As this is a basis, so by the help of linear combination of these two elements we can make R2. Again x comma y belongs to R2, so we can say x comma y can be formed by the help of these two elements. That's why we can write x comma y equals to some constant 2 comma 3 plus another constant 1 comma 0, where lambda comma mu are real numbers. You can consider here a comma b, c1 comma c2, whatever you can write here. Now come here. As it is x comma y equals to lambda 2 comma 3 plus mu 1 comma 0, if we do multiplication, it will be 2 lambda plus 3 lambda plus mu comma 0. And by adding, the result will be 2 lambda plus mu 3 lambda plus 0, that is 3 lambda 1. Now comparing, x equals to 2 lambda plus mu and y equals to 3 lambda. So as y equals to 3 lambda, lambda equals to 1 by 3y, and as x equals to 2 lambda plus mu, so x equals to 2 into value of lambda is this, y by 3 plus mu. So what is the value of mu? Mu equals to x minus 2 by 3y. Means we first consider two arbitrary constants lambda and mu, then we have to find the values of lambda and mu in terms of x and y. Now come here in this part. As x comma y equals to lambda 2 comma 3 plus mu 1 comma 0, let us apply linear transformation on both sides. We will have t of x comma y equals to lambda t of 2 comma 3 plus mu t of 1 comma 0. Now what is the value of t of 2 comma 3? It is given 4 comma 5. Just write here. Mu t of 1 comma 0 is 0 comma 0. Right here. Do simplification, you will get 4 lambda plus 5 lambda. 4 lambda comma 5 lambda. So t of x comma y equals to 4 lambda comma 5 lambda. Now what is the value of lambda? 1 by 3y. What is the value of lambda here? 1 by 3y. So t of x comma y will be 4 by 3y comma 5 by 3y. So the result will be t of xy equals to 4 by 3y comma 5 by 3y. So this is our required linear transformation. Quite interesting now. Now come to another example. Determine the linear mapping T maps R3 to R2. Here see, V is R3 and W is R2. Means our domain set is R3 and our codomain set is R2. Which maps the basis vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. This is basis for R3. How can you understand? Either it will be stated in the question or just see this is three-dimensional and each element has three components. So this is a basis for R3 to the vectors 1, 1, 2, 3, minus 1, 2 respectively. Means the linear transfer which maps the basis vectors means the linear transformation of this element is 1, 1, this element is 2, 3 and this element is minus 1, 2. So we can write t of 1, 0, 0 equals to 1, 1, t of 0, 1, 1 equals to 2, 3, t of 0, 0, 1 equals to minus 1, 2 and mark these three equations all together as equation number 1. These red circle numbers are actually my page numbers, nothing else. Let x, y, z belongs to R3. Since 1, 0, 0, 0, 1, 0, 0, 0, 1 is a basis of R3, again come to the point basis. Basis means these elements are linearly independent and by the linear combination of these three elements in different ways, we just consider linear combination and we can easily generate all the elements of R3. Or other words, you can say each and every elements of R3 can be expressed as some linear combination of these three elements. Again, x, y, z belongs to R3. So definitely x, y, z can be expressed as some linear combination of 1, 0, 0, 0, 1, 0, 0, 0, 1. So write it here. X, y, z equals to A, 1, 0, 0 plus B, 0, 1, 0 plus C, 0, 0, 1. You can consider here C1, C2, C3 or lambda, mu, xi, anything else. By simplifying, we get A, B, C. So we can say x equals to A, y equals to B, z equals to C. Mark these equations as equation number 1. This is our equation number A and this is our equation number 1. Now, let us apply linear transformation on this statement or this line. So result will be t of xyz equals to A into t of 1, 0, 0 plus B into t of 0, 1, 0 plus C into t of 0, 0, 1. Now t of 1, 0, 0 is 1, 1 by equation number 1. T of 0, 1, 0 is 2, 3, 2, 3. T of 0, 0, 1 is minus 1, 2 by equation number A. Now again doing simplification A, comma A, 2B, 3B, minus C, 2C. Adding A plus 2B minus C, A plus 3B plus 2C. Now what is A? A is X, B is Y and C is Z. So just putting them X plus 2Y minus Z, comma X plus 3Y plus 2Z by equation number 1. Hence the required linear transformation is T of x, y, z equals to x plus 2y minus z, comma x plus 3y plus 2z. So this is our required linear transformation. So in these two examples, I show how can we find linear transformations when 2 or 3 elements and their related transformations are given. So whenever you study linear transformation, you first study or you first see my previous videos, then come to the third video. Then only you will have proper idea about linear transformation. Now let us come to my next point or next topic, which is most important topic for this video, that is matrix representation or matrix of a linear transformation. I have to show this matrix representation or matrix of a linear transformation by few examples. Means we have to express the given linear transformation in form of a matrix, Let us explain by an example. A linear mapping T maps R3 to R2 be defined by T of x1, x2, x3 equals to 3x1 minus 2x2 plus x3, x1 minus 2x2 minus 2x3, where x1, x2, x3 belongs to R3. Find the matrix of T related to the ordered bases 1, 0, 0, 0, 1, 0, 0, 0, 1 and of R3 and 1, 0, 0, 1 of R2. Means this is our basis for this set R3 and this is our basis for this set R2. Now write down given T of x1, x2, x3 equals to this. Alright. So what will be the value of T of 1, 0, 0? The value will be x1 is 1, x2 is 0, x3 is 0. So simplifying we'll get 3, 1. Now we have to express 3, 1 in the form of 1, 0 and 0, 1 in this way. Right? Just see 3, 0 plus 1, 0, 1 by adding you will get this result. Right? Next is T of 0, 1, 0 means x1 0, x2 is 1, x3 is 0. Putting the values you will get minus 2, minus 3 and minus 2, 1, 0, minus 3, 0, 1 means the result we have to express in the form of the basis of R2. Similarly, T of 0, 0, 1 will be 1, minus 2, that is 1, 1, 0, minus 2, 0, 1. Now if we write these three results all together, then we will have T of 1, 0, 0 is 3, 1, 0 plus 1, 0, 1. T of 0, 1, 0 is minus 2, 1, 0 plus minus 3, 0, 1 and T of 0, 0, 1 is 1, 1, 0 plus minus 2, 0, 1. So what will be the matrix representation? First remember this concept. The mapping is T maps R3 to R2. It is given in the question. The mapping is T maps R3 to R2. Here the dimension of the domain set will be column and the dimension of the codomain set will be row. Dimension of the domain set is column and dimension of the codomain set will be row number or row. So definitely the result is or the required matrix is 3 minus 2 1 row wise, 1 minus 3 minus 2 row wise. Just remember we have to write like this way, 3 then minus 2 then 1 then 1 minus 3 minus 2, so that we have 2 rows and 3 columns. Okay, so this is the way we can express any linear transformation in a matrix form. Let us consider another example. Here T maps R2 to R2 be a linear transformation which maps 1, 1 to minus 2, 3 means the linear transformation of this element is minus 2, 3 and linear transformation of this element is 4, 5. Determine the matrix representation of T with respect to the basis. So definitely it is the basis for R2 as well as R2. So just write down T of 1, 1 is minus 2, 3 and T of 1, minus 1 is 4, 5. So this is our equation number A. These two equations are marked as equation number A. Now 1, 0, we have to express 1, 0 and 0, 1 in the form of these two elements, in the linear combination of these two elements, because we don't know the linear transformation value or linear mapping value of this element and this element separately. We just know the linear transformed value of this element is this and the linear transformed value of this element is this. We don't know the linear transformed value of this element. Then we have to find. The technique is 1 comma 0 can be written like this way, half 1 comma 1 plus half 1 comma minus 1. If you face any problem, you just do in your copy, you will get the result will be same only. Now let us apply linear transformation on both sides. T of 1 comma 0 is half T of 1 1 plus half T of 1 minus 1. Now we already know this value is minus 2 comma 3 and this value is 4 comma 5. Now doing simplification, minus 2 by 2 comma 3 by 2 plus 4 by 2 comma minus 5 by 2, not minus, plus 5 by 2. Adding this with this, the result is 1. Adding this with this, the result will be 4. Again, 1 comma 0 0 comma 1 is our basis for R2. Then we have to express this 1 comma 4 in terms of the basis 1 0 and 0 1, like this way, 1 into 1 comma 0 plus 4 into 0 comma 1, right? Next element is our 0 comma 1, that is half 1 comma 1 minus half 1 comma minus 1. Using linear transformation on both sides, T of 0 comma 1 equals to half T of 1 comma 1 minus half T of 1 comma minus 1. The value of this is this and the value of this is this. Again, doing simplification, we get minus 3 minus 1. Then we have to express this element in the form of 1 0 and 0 1 by this way. Okay, so what we get? We get T of 1 comma 0. T of 1 comma 0 is 1 into 1 comma 0 plus 4 into 0 comma 1, and T of 0 comma 1 is minus 3 into 1 comma 0 minus 1 into 0 comma 1. So what will be the matrix? The required matrix will be 1 comma minus 3 in row wise, 4 comma minus 1 in row wise. Just remember, we see here vertical, but we have to write like horizontal. So the result will be 1 comma minus 3 row wise, 4 comma minus 1 row wise. So this is our required matrix. So in these two examples, that is example number 3 and example number 4, I have shown how we can find matrix of a linear transformation. First one is R3 to R2, second one is R2 to R2. Now come to my next example, which is very important. Actually example number 4 is also very important, but example number 5 is reverse of the above two. Here matrix is given, we have to find the linear transformation. Okay, here matrix is given, we have to find the linear transformation. The matrix of a linear transformation T maps R3 to R2 related to the ordered bases 0 1 1 1 0 1 1 1 0 of R3 and 1 0 1 1 of R2 be this. This is our matrix. Find the linear transformation. So this is our basis for this vector space, and this is our basis for this vector space, and this is our matrix related to the linear transformation. We have to find the linear transformation. So write down the matrix of T is 1 2 4 2 1 0. Now T of 0 1 1, just remember the before one. See, we consider horizontal as vertical, horizontal as vertical. So definitely here horizontal will be vertical, horizontal will be vertical, just reverse, right? Here see, horizontal means 1 4, we have to write column wise, minus 3 minus 1 as column wise, vertical. So here the rows will becomes columns, vertical, 2 1 0 will be vertical, right? So T of 0 1 1 is 1 1 comma 0 1 comma 1. These two are basis for the codomain set, and these are basis for domain set. So what is the linear transformation of 0 1 1? 1 1 0 plus 2 1 1, that is 3 comma 2. Next T of 1 0 1 is 2 into 1 0 plus 1 into 1 1, that is 3 comma 1, and T of 1 1 0 is 4 1 comma 0 plus 0 into 1 1, that is 4 comma 0. Just remember this, horizontal becomes vertical, horizontal becomes vertical. Here see, horizontal 1 comma 4 becomes vertical, horizontal becomes vertical. So the linear transformation of this is this, this is this, and this one is this. Now to find the linear transformation, let x comma y comma z belongs to R3, means the domain set. Since 0 1 1 1 0 1 1 1 0 is a basis for R3, so definitely every element of R3 can be expressed as some linear combination of these three elements. Since xyz is an arbitrary element of R3, therefore you can say x comma y comma z can be expressed as some linear combination of these three. So we can write xyz equals to a 0 1 1 plus b 1 0 1 plus c 1 1 0. This is our linear combination. You can consider here c1 c2 c3 lambda mu gamma, whatever value you may choose, where ABC are definitely real numbers. They cannot be complex number because we are doing real algebra. So here this is linear algebra actually. So x comma y comma z equals to a into 0 is 0 only, a into 1 a plus a, then b plus 0, then b, then c, c 0, and if we add we will have b plus c, a plus c, a plus b. So x is b plus c, y is a plus c, z is a plus b. Now I add all the three equations like this way. 2 a plus b plus c equals to x plus y plus z. So a plus b plus c is half x plus y plus z. Now do subtraction one by one. A plus b plus c minus b plus c, that will be half y plus z minus x, because this minus x is this. Next a plus b plus c minus a plus c, the result is this. Then a plus b plus c minus a plus b, the result is this. So the value of a is half y plus z minus x, b is half x plus z minus y, c is half x plus y minus z. Actually this is the technique. First we consider the arbitrary constants a, b, c or lambda mu, then we have to find the values of lambda mu or arbitrary constants in the form of xy or xyz, etc. Now let us apply linear transformation on this statement or on this equation. The result is t of xyz equals to a t of 0 1 1 plus b t of 1 0 1 plus c t of 1 1 0. Now the value of this element is 3 2 plus b 3 comma 1, then c 4 comma 0, that is from equation number 1. Okay, just doing simplification you will get this result. Then you have to put the values of a, b, c from here in this part, you will get this result. Do this in your rough page and put the values here, because the problem is quite lengthy, or either you can do rough work here. Okay, so the result is t of xyz equals to 2x plus 2y plus z comma minus x by 2 plus y by 2 plus 3z by 2, by putting the values of ABC from these relations. Hence the required linear transformation is this. So this is the technique where or how we can find a linear transformation where the matrix of the linear transformation is given. And these two examples are the examples showing how we can find matrix of a linear transformation when linear transformation is given.